So, ja. Sieht ja ein bisschen aus, als wenn die Leute noch beim Frühstück sind.
Geh mal raus. Okay.
Also du brauchst nicht auf ihn zu warten.
Ja, okay.
Also sollte das der Fall sein.
Nee.
Soll ich nochmal für dich ein bisschen klatschen?
Kannst du machen, ja. Da kommen ja noch welche.
Said.
You're sharing.
Yes, yeah. I'll wait for you. Das waren dann gleich die ersten 5 Minuten von deinem Vortrag. Aber die kommen jetzt alle.
Das fühlt sich ja schon ein bisschen.
Ja. Okay, dann bin ich vorschlagen von morgen. Okay, good morning everybody. So the first speaker of this morning session is Peter Sollich, and his talk is on barrier crossing and rare fluctuations of active particles.
Thanks, Jürgen. Welcome, everyone. I guess I'm the beginning of the active classes session. And I think we have more biological talks after me. This is more on the StatMech end of things. I'm going to talk about some unpublished work that we've done with an ex-postdoc, Diego Tapias, who started this project and then been taken over by Rafael Diaz. And we've also worked with a bunch of very talented interns, Kartik, Leif, and Lars. Okay. So Smarajit sort of very briefly introduced the idea of sort of active particles and active glasses yesterday. Here's my sort of analogous but less text-heavy one-page introduction to active matter. So when we talk about active matter, broadly speaking, we think about particles that have some way of taking either stored or ambient energy and converting it into systematic motion, and this happens on all sorts of scales from very macroscopic to tissue level, and in fact even down to intracellular level. Silke, I'm sure, will tell you much more about sort of how to do this in a biologically, at least halfway realistic way. What's become very popular in the statistical physics community is to focus largely on self-propelled particles. Okay, so these are abstractions of bacterial swimmers. And so typically we model these as having essentially overdamped dynamics. For the moment, I'm going to look at single particles. We'll come to many particles later. And we have a sort of typical overdamped equation of motion with a kind of friction force, a systematic force from a potential, a thermal noise, and then here's the active bit. That's the self-propulsion force. If you think about this hydrodynamically, you might want to think more about a velocity rather than a force, but they're proportional up to factors of gamma, so it doesn't matter. The thermal noise has the usual properties in the sense that it's governed by, its variance is governed by some thermal temperature T. And then the interesting thing is this active force, which broadly you can characterize by two parameters. One is the scale, which I'll call F naught, and then one is the so-called persistence time, which is the time scale on which the correlations of this thing decay. And the fact that these correlations are non-trivial, they're not white noise like these ones up here, that's what breaks detailed balance. Okay, so we have a system which on the left has standard friction, but has a term on the right which is not consistent with that in the sense of fluctuation dissipation theorem. Okay, and of course, broadly speaking, what you expect is that for small torpy, this active force will work primarily like thermal noise, because if it's very short, has short correlations in time, then you can basically ignore that and just pretend it's white noise. Whereas if it's very persistent, then in the infinite torpy limit, you've basically got active forces that don't decay, and they just keep their modulus and direction. Okay? And so there are three very popular scenarios of realizing this kind of correlation function. And these are the standard, sort of by now relatively standard models. The first one is called active Brownian particles, where the active force has a fixed modulus, and it has a random direction. And if we do this in 2D, it's just specified by an angle, and the angle rotates randomly. And if you scale the Gaussian motion of the diffusive motion of the angle with 1 over square root of persistence time, you get exactly the correlation function from the previous slide. Okay. By the way, do stop me with questions halfway through. I mean, within reason, not like in Bulbul's talk. Okay. Another way of doing realizing the exponential correlations is in what's called run and tumble particles, where you have the same setup, but instead of having a gradually changing angle, you have an angle that's constant in time, and then it has it with a certain rate, which is precisely the inverse of the persistence time. The angle is randomized. And again, if you check, you get exactly that exponential correlation function. Or you can assume that the active force is a Gaussian process, and then you end up with something called the active Ornstein-Uhlenbeck particle, where the evolution of the force is just given by a restoring term, a corresponding noise term, and these are chosen so that, again, you get a variance, which is F0 squared, and a persistence time, which is this tau p. And then, of course, the modulus of this thing is now not fixed anymore, but it has a Maxwell distribution, just like velocities in the thermal system. Okay. So we're going to look at kind of these models. Primarily, I'm going to look at the first and the third, but if I have time, I'll come to the run and tumble case towards the end. Okay, so by construction, these models give identical mean square displacements, because the mean square displacement is just derived by integrating the force correlator. The structure, the factor, that has some differences already. In dense systems, certainly within the glass community, so far I think they've been largely regarded as sort of equivalent. And if you look at the level of an effective temperature, again, but just by integrating over the correlation function, you would assign the same effective temperature to each of those models. And it's just proportional to the variance and the persistence time. Okay? So then the one question that we asked was, well, what differentiates these models really sort of strongly at the level of sort of physical behavior? And of course, one obvious idea is to not look at sort of the average behavior that's governed by the correlation function, but to look at the rare fluctuations. Okay, and many other people have looked at this, starting at least with work in the sort of mid-2010s. So we're going to look at barrier crossing processes. Basically, in general terms, these are activated transitions between metastable states. There's many examples that we know where this is important, like chemical reactions, nucleation. And of course, for the purposes of this meeting, probably the most important case where we have transitions between metastable states is cage breaking or spontaneous plastic events in glasses. That's basically a many-particle system going from one metastable state to another metastable state, driven by either thermal noise or by active noise, right? And so these are the kind of processes we want to look at. Here there's some sketches of kind of how that works in nucleation, or if you just transition with 1 degree of freedom from one side of a potential to another one. And of course, we know very well how to do this in thermal equilibrium, where the transition rates are just basically given by the Arrhenius form, and they're governed by the potential difference divided by temperature. Here's a sort of typical trajectory that fluctuates between two minima, essentially realizing that scenario where the fast instances here are the transitions between the minima, and these are the fluctuations within the minima. So here we have a non-equilibrium system. As I said, we break detailed balance, so we can't directly use Arrhenius. So how we do this is then basically using path integrals. I'm going to tell you very briefly how that setup works. Then we'll look as a sort of warm-up at the case of not crossing a barrier, but just climbing up in the potential. And that's already useful in terms of comparing two of these active particle models, the active Brownian and the active Ornstein-Uhlenbeck model. Then as a sort of intermezzo, I'll show you something else that's quite non-trivial, that the escape paths in these models can break symmetry. And then we'll come to the many particle systems at the end. And if I have time, which I might not, I'll say something about run and tumble activation. Okay. Cool. So very briefly, how we do this mathematically is we describe the system by a stochastic action. So we assign a probability to a trajectory, for example, for active Brownian particles. That will be a whole time dependence of its position and its angle. And the probability of each such path is given by an action which has an associated Lagrangian. And this Lagrangian has this form, which is probably, if you've seen something like Onsager-Machlup actions before, should look familiar. If we start with the rotational part, that's just saying the motion of the angle is Gaussian. Okay, it's a Wiener process, basically. This diffusion coefficient is just the inverse of the persistence time, so the more persistent, the less diffusive the angle. And then this is just conventional stochastic motion with a kind of thermal diffusion coefficient D, where you have this conventional force from the potential, and then you have the extra active force. Okay? And we're going to look at the limit where you can make sort of analytic progress, which is the Kramers limit. So we're going to look at weak noise, so we're going to make both of these numbers small, so weak thermal noise and weak angular diffusion, but we're going to keep the ratio constant. Okay? And then from large deviation theory, there's a general result, which is also physically intuitive, which is that the escape rates are basically given by the probability of the most likely path. Okay, so what we have to do then is just find the path that has the smallest stochastic action, and that's in the weak noise limit gives us the scaling of the escape time. Okay. So that's all I want to say on the maths, basically. Then let me just show you one sort of simple example. This is an active Brownian particle starting from the zero of an anisotropic harmonic potential. So the contour lines here give you the equipotential contours. So you see they are elliptical, so we have different curvatures in the two directions. We start at the origin, and we fix the point here that we're going to climb up to. And we're just going to find the path that has the minimum action. So what will the particle, what's its most likely way of going from the minimum to this point up here? Okay? And then what you see as you vary this d theta, so the persistence of the particle relative to thermal diffusion, which is not written explicitly here, then you get a significant dependence of how the particle does this job of climbing up to that point. And in fact, the paths look rather strange, right? So they have these kind of kinks here, which are actually real kinks, right? And they depend significantly on persistence. And so while that looks rather unintuitive, it actually becomes relatively simple if you look at what's called the effective potential, because as long as the angle of the self-propulsion is constant, what the particle is basically doing, it's moving in a constant potential, right? Because as long as the angle is constant, I can take that constant force and I can include it as a linear term in the potential, okay? And so if I plot the contour lines of that effective potential, right, what you actually see is that what's happening here is that the particle is basically actually descending in that effective potential, right? And then from here, it's actually performing the thermally activated part of its trajectory, right? So these are kind of instantons in a slightly unusual sense. They have two pieces. The first piece is basically the particle goes as far as it can using just self-propulsion, and then it does thermal activation, okay? And the reason why there are kinks here is basically the particle takes a long time to slide down here, and then here it waits and then it thermally activates to get out of that minimum of the effective potential. Okay? So that's already kind of an unusual feature that we see here, that basically, because we have the self-propulsion with a fixed modulus, the instantons, they are in these kind of two parts, where you go as far as you can without thermal noise, and then you climb up the rest of the potential to go to where you want to go. Okay? So that's just to provide a little bit of intuition. We can then actually also work out the activation barrier fairly simply, because the descent part, if you want, doesn't actually cost any probability, because that's the most likely path. The particle will just keep its self-propulsion and just go as far as you can go up the potential without needing thermal noise, right? And so then in stochastic terms, you only pay for this part of the trajectory outside of this dashed ellipse, which is the locus of all the minima of the effective potentials for different orientations of the active force. Okay? And then, yes, of course.
So what exactly is happening after it reaches the minimum? Is it still moving actively, or is it like moving through thermal fluctuations? That part is not clear to me.
So there are always thermal fluctuations, but what the particle does, it basically moves athermally. That's the optimal thing to do. So it keeps its propulsion force constant, it moves as far as it can go with that, and then it waits for a thermal fluctuation.
And then it goes up.
And then it goes up. Okay, so and where that changes here on this dashed line.
Okay,
right? So the instanton has these two pieces. You first go athermally, basically, and then you wait for a thermal fluctuation. Okay, and then if the particle is very persistent, which is this line here, then because the angle isn't changing, we can actually show that the action that you need is actually literally just a potential difference in this new potential, in the effective potential. So we can very easily work this out explicitly. Okay. Okay. So that already gives us an interesting comparison with what happens for the other very popular type of active motion, which is the active Ornstein-Uhlenbeck particle. Let me just work this through for you briefly for an isotropic harmonic potential. And let's say we want to climb up to some position R0, okay? Then what we've just seen is that in this case, the quantity that determines the scaling of the escape rate, so the minimum action, right, is just governed by a potential that's this potential, but you go as far as you can with the active force. So basically, you only have to climb a distance that was reduced by the active force. Okay? So it turns out that that's the expression for the remaining piece of your trajectory that you actually have to climb using thermal motion. Okay? And then for the active Ornstein-Uhlenbeck case, this has been looked at by many people. In the harmonic potential, you can work out exactly what the probability distribution is in steady state, and therefore you can get the effective action that governs how long it takes you to get to a certain point. That's the general expression, which depends on thermal temperature, how far you need to go, and your active parameters. And if you take a strongly persistent particle, then you see you have a torp here over torp here, which cancels. So what remains is just, again, the variance or the scale of the active force. Okay? So then if we compare these two expressions, well, you see that generally the active Ornstein-Uhlenbeck particles are faster without thermal activation, because here I can take T to 0 and I still have a finite action, whereas up here this thing blows up when temperature goes to 0. So the active Ornstein-Uhlenbecks don't need thermal noise, and that's because they can wait for a fluctuation of the active force. Right? So basically, with an active Ornstein-Uhlenbeck particle to climb, you can just wait till your active force gets large enough. You don't need thermal noise. That's the intuition. Right? Whereas with an active Brownian particle, of course, you're limited in how far you can go. Then you need thermal noise to go further. Right? Of course, the active Brownian particles do have an advantage, right? Because when your force allows you to go where you want to go without any thermal activation, then of course you don't need, basically this activation barrier becomes 0, and you have a sort of non-exponential scaling of the escape. Okay, so we end up with a sort of fairly simple phase diagram which looks like this. If we just compare these kind of speeds of climbing to a certain point in a harmonic potential, here I've got temperature on one axis and the modulus of the active force. On the other axis, I'm looking at the highly persistent limit. That's why there's no persistence time in the diagram. And basically, you see what I mentioned earlier. At low temperatures, generally, the active Ornstein-Uhlenbeck particles are faster. Over here, that's the sort of maximum force you need. So over here, the active Brownian particles are faster, right? And then there's an interesting shape down here, which is that this phase boundary is linear, right? And this basically comes from the fact that both of these barriers in the small t and active force limit, they scale as functions of f0 divided by t, and that's why you get a linear phase boundary there. Okay, so this is sort of interestingly also, for example, at constant temperature, this is sort of re-entrant, right, in the sense that at small active force, the ABPs are faster and then become faster again at high active forces. Okay, I need to drink something, so if you have questions, you can think about them now. Okay, 1, 2, 3, maybe.
So this is true for kind of any d theta over d ratio. I know you're working in the limit of both small, but
Yeah, so this is the highly persistent limit, so d theta is small compared to d.
okay.
Yeah, I mean, I had a related question. Like, if you have, let's say, a less persistent active particle, then would you be able to write this in terms of an effective potential? Because the d theta will be so high that you cannot really treat the force as a constant, correct?
Yes, so the effective potential mapping only works, strictly speaking, in the persistent limit, which is what I'm mainly going to focus on, because the other limit is kind of the boring one, because it's the effectively thermal limit, where all the different activity types become equal.
Sure.
Okay, so the more interesting limit is that persistent limit, but that's really only also the limit where this effective potential mapping works. Yeah.
Sure. Thanks.
Yeah, so that d theta tends to infinity, that case I didn't understand, like how you are getting, what does it mean actually?
So this is looking at d theta going to 0, so that means infinite persistence time.
No, the previous one, you showed some trajectory for d theta tends
Yes,
to
so
infinity.
the other
Yeah.
case where basically the persistence is not relevant, because basically the particle does not, there's no decrease in probability for changing angle, basically. That was done by Royer et al. So with Julien Tailleur, etc. So that's this trajectory. Okay, so there is in that limit, what basically happens is that the angle is slave to kind of the rest of the trajectory. Okay, so basically here you don't pay for changing the angle. Okay, so what the particle does, it chooses its self-propulsion in the right direction at every instant. In that case, you can write down a reduced action which doesn't contain the angle at all, right? And that's done in this paper. Okay, so let's look at the this kind of interesting extra feature that the active particles have, which is that they can break symmetry. Okay, so let's look at more interesting potentials now. Let's take a simple symmetric double well. So this is, I've taken everything symmetric here, as symmetric as I can, equal potential height left and right, and the potential is also symmetric on the plus minus y, right? And of course, we know what your typical thermal activation process will do. It will go through the middle. That's where the lowest barrier is, and there's no reason to break the symmetry here, right? Okay. And then you wouldn't have me talking about this if nothing more interesting happened with the active particles, and it turns out if the self-propulsion is strong enough, they end up doing something like this, okay? So that ends up being the optimal path. Sorry, for the V0 here, read F0. We weren't quite consistent with the notation there in the plots, unfortunately. Okay. And so for low modulus of the self-propulsion, it turns out you do go that symmetric path, but if the self-propulsion becomes strong enough, then you can actually go sideways, okay? And then you look at this for a second and you think, well, what the hell is going on there, right? But really the intuition, again, is not too complicated. What we have here is a potential that has relatively low curvature at the barrier. Okay. Now, if I go sideways, that means I'm sort of tilting the potential that way. Okay. I'm not sure whether you can imagine this. I'm tilting the potential in the y direction, right? And depending on curvatures here and here, that means this barrier is coming down more than the minimum is changing. Okay. And that way you can reduce the activation barrier, right? And in fact, this transition that we see here from symmetric to asymmetric paths has all the kind of standard features of a sort of standard phase transition. We can look at, in the persistent limit, we can look at the action versus the angle. It looks exactly like your familiar friend, the Landau theory of second-order phase transitions, right? We have the angle at which the particle sort of executes its path has exactly that sort of second-order shape. Okay. But then depending on potential parameters, we can also have other scenarios. Okay. So we can have a first-order transition scenario where as you change the strength of self-propulsion, which is on the x-axis here, your optimal angle jumps discontinuously. So there's at some point where you go from the symmetric path to one with an orientation of the self-propulsion that has changed discontinuously. Right? And of course, then there's also metastability around that transition. We can push this a little bit further. So as a function of self-propulsion force, again, this is F0, sorry for the notation there. The lambda is a parameter that determines curvature at the barrier in our potential. And so you have a phase diagram which has a tricritical point. You have a first-order dynamical phase transition up here. You have a second-order dynamical phase transition. Each time, as you go in that direction and you increase the self-propulsion, you go from the symmetric path to the asymmetric path. Okay? So this is a dynamical phase transition that has all the sort of features of a usual equilibrium phase transition. And then, of course, you can also do this with finite persistence. So far, I've looked at this d theta equals 0 limit, and we've gone up this way by increasing self-propulsion. You can also get the same transition by decreasing persistence. And again, that tends to break the symmetry of the transition path, right? Because as you make the motion less persistent, it's easier for the particle to go sideways around the symmetric path. Okay. So here's the transition at finite persistence. So this is now a fixed self-propulsion forces, different persistent times, basically, and you see that for the strongly persistent motion, the particle in this case goes symmetrically. Otherwise, it has this sort of sideways motion. And if we plot as a function of inverse persistence time the optimal angle, you see it has this jump, and there is this kind of metastable region, which incidentally also means around that persistence time, you will see coexistence of those paths. So you'll see both types of motion, right, because it's a first-order phase transition. Okay, so having done all that, let's look at the many-particle systems. This is going to be very brief because I'm not going to show you any of the calculations, but the results are fairly simple. Okay, so basically what we can do is we can take everything we've said now about single particles, and now we're going to just generalize this and assume now that this vector R is just a configuration of a system of active particles. Okay, so in general, in two-dimensional space, this would now be a vector of dimension 2n, right? The V of R would now be the interaction potential, okay? And it turns out you can do a similar calculation that we just did to find what's called the quasi-potential, which is basically how likely you are to get to a certain point in your local potential well, which also then at its local maximum tells you how likely you are to escape, right? So this is the sort of thing that in thermal motion would just be the actual potential up to a factor of 1 over temperature. Okay, and so it turns out for the active Ornstein-Uhlenbeck case, this is actually a relatively simple, although variational expression. It turns out that the quasi-potential is the effective potential I had before, except we reset it now so that we subtract the minimum. So its minimum is at 0, okay? And then we have an extra term, which basically means you pay for having a large active force. And of course, the fact that this is quadratic comes directly from the fact that we have an active Ornstein-Uhlenbeck system where the distribution of the active force is Gaussian. So you expect a quadratic penalty in the probability. Yeah?
So what you call f is a vector now. So this is all of the f's. So you have the angles baked in implicitly.
Yeah. So now each of the particles has a two-dimensional force vector. So this is a 2n dimensional vector that we have to optimize over in principle, right? And this has the zero temperature limit of this is kind of the n-dimensional generalization of things that Alan Bray and Alan McCain have done a long time ago. Also, Boyer and Tailleur and co-workers looked at this more recently. And then actually I should mention Atsushi Ikeda is also looking at essentially that scenario, and they have some very nice simulation results for the athermal limit, which also confirm this kind of. In the athermal limit, you can show that basically you always have to be at the minimum of this effective potential, and that means that the force is just the gradient of your potential, and your penalty term just becomes the gradient of your potential squared. So in the persistent limit, athermally, your effective potential is essentially just grad squared of the original potential, right? Because what's relevant is basically how much force do you need to get to that point. That's what you pay for stochastically, and that's therefore what governs the escape, right? And then we can do the same calculation also in higher dimensions for the active Brownian particles. And there's basically only two changes. One is that, of course, we can now only tune one angle per particle. The modulus is fixed, so I've written it schematically just as F0 again. Okay? And we don't have a penalty for the modulus of the force because the modulus of the force is fixed anyway. The only thing we can play with is the angle, and all the angles are equivalent. Okay? So that's actually essentially the same formula I had before. Again, you just get this effective potential, and it's divided by T. Okay. And then you can take these general expressions, and you can work out what is the
I have a question. Sorry.
Yeah.
So in the earlier case, for tau phi finite, you had some effective temperature for active on-stimuli ligament, right?
Yeah.
So here, what happens to the effective temperature if you have tau phi finite?
So this result we can only derive in that simple form for infinite tau p. So I cannot tell you directly what the finite tau p corrections to this are. Of course, what you know is that for small tau p, this has to cross it back over to a thermal system. Okay. So you can basically write down an interpolating form that has this for large tau p and the thermal form for small tau p. Okay. And that turns out to be exact in the harmonic potential case that I showed you earlier. Right. But we don't know the full tau p dependence of this result. Okay. This is only the infinitely persistent limit.
So do you think that T effective will have some effect from interaction?
Well, what you can definitely already see from this is that generally there's no effective temperature, right? Because the functional form of this, as I said, for example, in the athermal limit, involves not the potential V, but involves the gradient squared, right? And that's, of course, is a different potential, right? So you can already see that this general idea of an effective temperature is not going to work in general, right? In the harmonic case, of course, those two things are equivalent. I mean, they're equivalent in 1D, they're not even equivalent in higher dimensions because they have different anisotropies in the potential, right? But the effective temperature idea generally doesn't work, right? You have to use something like this. Okay, I should try and finish. So what we can easily do on the basis of these expressions is, for example, we can look at the weakly active limit, right? And we just do basic perturbation theory for small f0. And then what you find out is that the correction to the thermal barrier for the active Ornstein-Uhlenbeck case, this one here, just scales quadratically in the active force. And for the active Brownian particles, it scales linearly, okay? And that shows you that actually the phase diagram in higher dimensions has to look quantitatively like the one I showed you for the harmonic case, right? Again, you see that for zero temperature, the active Ornstein-Uhlenbeck particles are going to be faster in general, right? Because in the ABPs, the barrier always blows up when temperature goes to zero, right? And you can also, from these scalings, deduce, again, that you're going to have this linear shape of the phase diagram here, okay? So that's kind of nice about this generic calculation is that we can do this in high dimensions, and this kind of competition between thermal and active effects has the same trade-off between the two types of particles in the generic case. I think I've got 1 minute to finish. So I'll tell you very briefly what happens with the run and tumble particles. Let's ignore the maths. So basically, I'll just flash up this result. What you can show is that if you have run and tumble particles, they always have smaller activation barriers than ABPs. And this is based on a result that we derived earlier for one-dimensional activated processes due to non-Gaussian noise, because what you have in a random tumble particle is the angular motion is not Gaussian. So you have Poisson shot noise, where you have large angular changes with a certain rate, and on the same basis, you can prove that the random tumble particles are always more efficient than the ABPs. Okay, time for the summary. So we started by looking at these single ABPs, which have these interesting instantons that start with basically what's effectively a descent in an effective potential. We looked at this generic phase diagram that compares how quickly these two types of particles, the ABPs and the AOUPs, escape across some barrier. We looked at the fact that they can break symmetry and the fact that the run and tumble particles and their generalizations are always faster than the active Brownian particles. Some of the things we're looking at the moment is actually what does the optimal escape look like for run and tumble particles, because given that these particles can tumble, you would expect that they make use of that when they escape, and we have some evidence for that. Of course, one can compare with simulations. There are some simulations, especially for AOUPs, and I already mentioned Atsushi Ikeda's and collaborators' work who've looked at this more systematically recently. I think that's going to come out very shortly. And then, of course, what we really want to do is then, which is also probably the most important thing for this meeting, is to look at the active class dynamics that follows from these results, right? So what actually happens in the many particle systems when you combine this with the collective motion of all the particles, not just looking at a single transition. And that's where I'll end. Thank you very much.
Thank you very much. Questions? I think you...
In the single particle case, if you include some amount of anharmonicity, does it affect the escape process, or in what way?
At the anharmonicity does matter.
Yeah.
And I mean, in fact, these results here, of course, they're also valid for one particle. Right. So you can reduce this back to one particle, and this, in principle, then gives you the generic shape of this effective potential. And as I said, for the AOUP, it basically, as you increase the strength of the active propulsion, you cross over from something where the effective potential is V to something where it's basically grad V squared. Okay, and then you have you basically interpolate between these two shapes. So that's how the anharmonicities come in.
Hello. Sorry, a question?
Yeah.
It's on the back.
Go ahead.
So I go?
Yeah.
Oh, it's Peter. The chairman said to go ahead to me. Sorry. But I can wait. I can wait. No, I was wondering if you can say something about nucleation. I mean, so this is the many particle case. So how nucleation is changed? So imagine that you have particle and you have two stable states in a spatially extended system. How nucleation would be changed by this kind of noise?
That's something we haven't worked out yet. I think that's a very good question. I mean, I think in principle, as long as you can think of the nucleation sensibly, that's not something I've really done. As really a metastable transition from one single many particle configuration to another one, then this kind of setup applies, right? Now, of course, with nucleation, one has to be a little bit careful because specifying whatever a critical nucleus, that's not necessarily a single many particle configuration, so there might be sort of entropic factors, right? Because you can have sort of many intermediate states or something. So that I haven't thought about, right? But in principle, this should tell you also what's happening in nucleation. But then one would need to do is basically translate this change from the kind of interaction potential being V to grad V squared into, for example, effects on the surface tension of the nucleus, etc. Right? So I think that's an interesting question, but it's not something that we've done.
The initial condition for AOUP equations,
yeah,
equation of motion is the active force F is equal to 0, right?
Yes, because you can show that basically if you write down the kind of Euler-Lagrange or Hamilton equations that come from this optimal path condition, that the force always, if you go backwards in time, it has to go to 0 exponentially.
Yeah. And then in the infinite persistence time limit, it stays to be 0.
The active force? No. So what happens is that the most likely path that you get to that realizes this quasi-potential, and this actually was worked out in 1D also by Boyer et al., for example, is one where the force increases exponentially on the time scale of the persistence time. Okay, so basically what you need to do for the analysis, you need to rescale the time, and then in units of persistence time, the active force increases exponentially until you make the transition, and then it decreases again exponentially. Right?
Okay.
Yeah. Because you need the active force in the athermal limit to get you over the barrier, right? So it cannot stay 0.
Okay, let's not say in athermal limit, just in a normal, when we have the background thermal noise as well.
Then it depends on the competition of F0 squared and T, right? So basically if F0 squared divided by T is large, right, then you basically it's self-propulsion governed, and then the active force needs to have a large value at the transition. As you make the thermal effects bigger, then the active force, even at the transition, ends up being quite small. Okay. So then how big it is just depends on that ratio of F0 squared and T, basically.
All right.
So if I look at the form of the quasi-potential, at t equal to 0, it will blow up, right? So which would mean that there won't be any escape, but that kind of is contradicting what you just said.
Yes, but you could basically, what happens in the, sorry, I think the 1 over t, actually, sorry, that's a typo. The 1 over t is only on this term.
I see,
it's not
okay.
on the second term, sorry.
Okay.
You've spotted the obvious error there. And so what happens is because of the 1 over t there, you end up minimizing this to 0, and that's what links the force to the gradient of the potential. Thanks for noticing that. Yeah, so the 1 over t in this should be only on the effective potentials. Yeah.
First you, and then she.
Thanks, yeah. Very interesting. So as Anil showed many years ago, with infinite persistence time, you should get some sort of system size length scale in there. How does this interact with your barrier?
You mean, for example, in the sense of velocity correlations, etc.?
Yeah, exactly.
So here we're, of course, not looking at the typical motion, right? We're looking at kind of rare events, and so the kind of the correlation lengths that you get in the typical dynamics don't really turn up here. I mean, I haven't really worked out whether there are strong correlations in the way you would cross this transition path, but it is quite likely, right? Because what happens here is that, as I was just saying in response to the other question, is basically all the active force components increase in this at the same rate to get to the final value in the athermal limit, right? And so that means that basically the motion of all the particles is slave to 1 degree of freedom, right? So I think it's likely, if you looked at this in space, probably that there are large correlations, but that's, again, that's not something that we have done, but that's a good question. No.
What's your next step if you want to do actual glassy dynamics here?
Well, part of the next step actually has been done by Atsushi already, right? Because you can take this setup, right, in a many-particle system. You look at a process which takes you from one metastable state configuration of the glass to another one. So you look at a cage bridging process or a local rearrangement, right? And then you work out the activation barrier, right? So that's exactly what this is, right? This is already glassy dynamics in that sense, right? Because this is telling you what is the activation barrier for going one particle configuration of a glass actively to another one, okay? So it's basically telling you how are the activation times for breaking cages, etc., how are they modified by self-propulsion, right? So because you can do this for the many particle system, as I've tried to explain on this slide, right, you're already in the right setup for that, right? But of course here, everything I'm talking about is kind of for one specific initial configuration and one final configuration. Then of course one has to look at this statistically, but Atsushi has done this, and I mean, they find, for example, exactly the scaling with grad squared of the interaction potential for the activation barrier, right? 0T, right? Because of course, so 0T is the case where you can solve this exactly, right? And you just get this grad V squared form, right? So that's the easy case, right? So it's, I mean, it's already connected, right? But of course, I mean, I think what would be interesting is not just to do it for the athermal case, but actually explore the whole phase diagram, where it's a bit more complicated. But like I say, Atsushi has already got results for the kind of for the athermal line of this. Right?
So maybe in the interest of time, let's move on. Let's thank Peter again for this very nice talk. And the next speaker is Saroj Nandi.
So I'll disconnect everything.
Am I audible? Thanks, Jürgen, and thanks Rituparno, Sayantan, Ranjini, and Srikant for the invitation. I'll be talking about a constitutive model for the discontinuous shear thickening in a tissue monolayer. This work is done in collaboration with my colleague from TIFR Hyderabad, COVID, and it is done by Tolmoy, who is present in the audience. Now, epithelial tissue is a monolayer of tissue. It's a confluent monolayer where the cells entirely cover the space. So that's the confluent meaning. And it acts as a protective barrier for most of the organs, like the skin or any organ, if you can think of. This outer layer of cell is known as the epithelium tissue. And therefore, because it needs to act as a protective monolayer, how it keeps integrity under external shear or external different type of perturbation is very crucial for proper biological function. And also in the several other contexts, the rheological properties of such a system is very crucial, for example, during development and morphogenesis. Now, I'll show a couple of examples where the recent experiment have looked at the rheological properties of these systems. And these two are from the lab of Guillaume Charos, where they looked at this MDCK monolayer, and although it's one layer of cell, it can actually withstand large deformation. So it is being pulled in this direction, and eventually it will fracture. So it has started fracturing now. And yeah, it can, so this is the healthy monolayer, wild type, healthy monolayer. It can actually withstand large deformation. On the other hand, when they, so when they treat it with a particular drug known as caliculin, so which basically increases the contractility in the system. In this case, they basically pull it and then hold the two bars in their position. So this is under stress. And then this contractility of the monolayer increases, and then it starts rupturing. So this is the drug-treated monolayer. Another aspect where during development, large-scale cell flow is very crucial. So this is the movie for the neural plate formation during the zebrafish gastrulation. Here there's large-scale flow of the cells from the two sides, and then they go into the third dimension, and that is very crucial for this development process. This movie is taken from this lab of Michael Smartney. Now, the theoretical description of such a confluent monolayer, one of the aspects that is very crucial for these monolayers is the constant of confluency. That is, the cells need to entirely cover the space in the healthy condition. So there are three snapshots that I have shown. This is for the Drosophila wing disc, MDCK monolayer, and MCF10A, three different types of cell monolayer. And this particular constant that the cells must cover the entire space leads to this very strong geometrical constant, and that needs to be taken into account. The other aspect is that for most practical purpose, the mechanical property of a cell essentially comes from a thin layer of cytoplasm just below the cell membrane, and this is known as the actomyosin cortex. It consists of some rod-like molecules known as actin, and then there are myosin molecule. The myosin molecule basically pulls two of these actin filament, and then they pull towards each other. And this is essentially one of the dominant mechanism of force generation inside the cells. And so this is one of the aspects for the mechanical purpose. And now if we are looking, here we are looking from the top of the cell, but if we are looking from the side, then the cells also have some height. And then there are different cell-cell intercellular junction molecule. There are typically three types of such molecule, known as the tight junction molecule, adherent junctions, and desmosome. And these can be treated as intercellular interaction, and they also need to be taken into account. And further, there can be interaction with the substrate via different type of focal adhesion. Now, this type of model, they basically represent the cells as polygons. So these are two-dimensional model. The height of the cell remains nearly constant, and that allows a two-dimensional description of this system. So these models, they represent the cells as polygons and with a preferred area and perimeter. So the source of this preferred area is as follows. The cells, okay. So, all right. So cytoplasm can be treated as a incompressible fluid, and there have been many type of experiment where it has been shown that this description as an incompressible fluid actually works quite well. And one can look at this reference. So this incompressibility, so this constant volume of the cytoplasm, and that the height does not fluctuate much, these two constants one can include in an energy function as AI minus A naught. So AI is the area of the cell, and A naught gives the target area. So this basically any fluctuation from the target area will cost energy via this Hamiltonian. Then there is this cortical property. So these myosin molecule try to pull these actin filament that tries to minimize the boundary of the cell, and that we can include as a lambda p times pi square. And then there can be cell-cell adhesion that basically tries to increase the perimeter, and that we can include as a attractive term minus k times pi, and pi. So this must be proportional to pi because for the cells, the interaction can only happen at the boundary. So must be proportional to pi. And this constant, we can write it as 2 lambda p times p naught, just to match with this. And then all these three terms I can write in the Hamiltonian. So this area term comes because of this. And these two terms and include a constant in the Hamiltonian without any other cost. So I can write it as lambda p times pi minus p naught square. So this is the Hamiltonian that I get, where lambda A and lambda p give some area and perimeter moduli. AI is the area, pi is the perimeter, actual perimeter of the cell, and then A naught is the target area, and p naught is the target perimeter. Now, p naught is very crucial parameter for this system, and most of these interesting property, they come because of this p naught that I'll show in a while. Now, given this energy function, we need confluent models, and there are several types of models. Some of them are continuum, some of them are discrete lattice-based models. So these continuum models, such as vertex model, Voronoi model, phase field model, etc. And there are also lattice-based model like the cellular pots model on different types of lattices. Now I'll go through a slightly more detail of the vertex model and the Voronoi model because they will be important later on. So, but before that, we can write this Hamiltonian in a slightly scaled form, where I can set this area, target area A0 to 1, and in that way I can rescale all of these terms such that lambda A remains lambda A, H I can rescale by this A0 square, and all the others get rescaled with this A0 with their dimension, like AI becomes capital AI by A0, and the perimeters get scaled with square root of A0. So in that case, I can compare different systems. So small p0 basically plays this role of this perimeter now. So in the vertex model, there are these vertices of the cells that are the degrees of freedom. So I need to evolve the system via these vertices of the cell. And then there is a connectivity matrix, this information that essentially connects different vertices, and this leads to this, this polygon. And this, now I can do this for the entire system, and this will give different type of different polygons. So each of the polygon will have this target area, actual area and perimeter. And given this area and perimeter, now I can use this energy function to calculate the force as the gradient of this energy function, and then I can evolve the system with the gamma being the friction coefficient, and Fi comes from this energy function, and then other type of forces like the active force Fia and thermal force Fit. And this is a movie from our vertex model simulation. Now, one of the aspects which is very crucial for the vertex model is known as the T1 transition. Now, it's possible that the two vertices come very close to each other, and then they eventually can cross. But if they cross, then that's the end of it, the model breaks down. So we'll have to be very careful not to allow that. And we'll have to define a parameter L0. When two of the vertex becomes closer than this L0, such that the L becomes smaller than this value, then we flip this, this edge, and then again rewire these vertices. So earlier when 1 and 2 was not nearest neighbor, but 3 and 4 was nearest neighbor. So after this T1 transition, 1 and 2 now become nearest neighbor, and 3 and 4 go away from each other. So this is known as the T1 transition, and L0 is a model parameter that we need to carefully define. Now, by contrast, in the Voronoi model, there is these Voronoi centers of the cells are the degrees of freedom. So in this case, given these Voronoi centers, we do a Voronoi tessellation, and then from the Voronoi tessellation, we get each of these polygons, and from these polygons, I can again get this area and the perimeter, and then I can calculate again the force, and given the force, I can evolve the system, and in that way, I can get system properties. Now, compared to vertex model, this T1 transition in this model is implicitly included. So we don't need to give all of these L0 or any of these parameters. This is taken within the system. Each time step, we'll have to do the Voronoi tessellation, and that will give the T1 transition all by itself. Okay, so these models are biologically relevant, but apart from their biological relevance, they are actually interesting by their own rights as well. And it has been studied quite extensively in the last decade or so, and it is quite popular in the biology community as well. So one of the results, it has been shown that there is a shape-driven fluid-like to solid-like glass transition in this system. And this is for the self-propelled Voronoi model, and these results I'm showing from the group of Lisa Manning, Max B, etc. And this is this AVP type of activity. So Fia is V0 times Ni. Ni is the direction of the self-propulsion, and theta I here does a rotational diffusivity, with the diffusivity being dr. And these are the mean square displacement at the 2-point correlation function, FSKT, K at the structure height maxima. Now here, notice one thing, that given a, so this is zero temperature simulation, and given a particular value of this activity parameter, if I increase this P0, then the dynamics changes. So with increasing P0, the dynamics becomes faster, mean square displacement becomes larger, and FSKT decays much faster. So given P0, there is this fluid-like to solid-like transition at a particular value of P0, which is around 3.81. Above this, it behaves like a fluid, and below this, it has this solid-like behavior, and this they have identified as the rigidity transition within this model. Now, this has also been tested in experiments. So this is data for these bronchial epithelial cells. This side is non-asthmatic and this side is the asthmatic cells. As the cell matures, so the dynamics becomes slower, it becomes more glass-like, then this observed shape index, which is related to P naught, that goes closer to this 3.81. And also, in the asthmatic cell monolayer, the dynamics is faster, and they also observed that the shape index is actually larger in the asthmatic monolayer compared to the healthy monolayer. So this is taken from this paper that appeared in 2015. So now let's look at this rheological property, and this is a simulation from the vertex model where we are applying shear in the x direction and the gradient of the shear in the y direction. And this is stress as a function of the strain. Now each time there is a drop in the stress, there is a T1 transition in the model, because T1 transition is the only way that the system relaxes the stress in this system. Now if we look at this vertex model data that Tanmoy has produced, sigma as a function of gamma, and also very similar data is also observed in the Voronoi model, and this Voronoi model data is from this paper. So there is one particular aspect that for some of the systems, some values of P naught, sigma increases, so let's look at close to this gamma tending to 0. So sigma increases with increasing gamma. But there are some certain other values of P naught where sigma remains nearly 0 up to some critical value of gamma c, and then it starts increasing. So if I define this elastic modulus as this derivative of sigma with gamma near at gamma tending to 0, then there will be some value of P naught where P naught are larger typically. So then the elastic modulus will be 0. But for smaller values of g, this g will be non-zero. And it turns out that this damming transition from this separating this g equals to 0 to g non-zero value, that also coincides with the rigidity transition that they observed in the context of glass transition. Now there is an unusual property of this jamming transition in this system, that if we now look at this steady state property, in the liquid property, then sigma is a function of gamma, so it first goes, it increases, then it yields, and then it becomes this liquid state. And this particular saturation value of sigma, it depends on the gamma dot, this rate of the shear. And now if I plot this steady state value of sigma as a function of gamma dot, then they have this type of behavior. Now if I feed it with a Herschel-Berkeley form, then I can get this yield stress, and this yield stress is plotted for this vertex model here, and this has very linear type of behavior. If I feed it with a linear form, then I see that there will be some value of P naught where it goes to 0. And a very similar type of behavior is also observed in the Voronoi model that taken from this paper. So it goes to 0 at a value where it is higher than this jamming transition. And the jamming transition happens around this value, and here sigma y is non-zero. So this gives three different regime for this system. At smaller than this 3.81, both g and sigma y are non-zero. At very large value of P naught, both g and sigma y are 0. But there is an intermediate regime where g is 0, but sigma y is non-zero. And this regime is quite interesting, and it turns out that in this regime, we actually see discontinuous shear thickening. So here again, data for this active vertex model with rotational diffusivity equals to 0.5. When in this regime, low P naught regime, where g and sigma y both are non-zero, then we see that it shows only shear thinning. There is no shear thickening. But in this regime, sigma increases, but very small value, and then there is a sudden increase in sigma, and then it goes to the solid-like regime. And this discontinuous shear thickening is observed only in this regime. And okay, now discontinuous shear thickening has been studied quite widely in the context of dense granular suspension, and here I have shown some of the papers. So here this accepted mechanism is as follows, that it observed in the suspension, and there is this liquid that is in between two fluids that gives the lubrication layer. So that leads to this frictionless rheology, and eventually at high stress, this lubrication layer goes out, and then the two particles, they come into contact with each other, and that leads to this frictional rheology. And this interpolation from frictionless to frictional rheology leads to this discontinuous shear thickening. So the basic requirement in this system, in the dense suspension of granular systems, that there is a suspension, there is a liquid that leads to this frictionless rheology, and then the squeezing out of this liquid that leads to this frictional contacts and friction. So the mechanism can vary, but
always the repulsive force that keeps it apart.
But you need the liquid, right? The suspension. Only in one component? Yeah.
Unless you have a repulsive
Okay. Okay. So the main point is that it needs to be suspension. You need to have a frictional to frictionless to frictional rheology. This is important. And now in this system, the confluent system is quite different from that perspective because there is no intercellular space. So there is no space for liquid. And the system is always confluent. There is no solvent. Also, the system is quite defined in the sense that there is many-body interaction potential in the system. But the result that I have shown is for active system, and activity can have very non-trivial effect. So one question is DST observed because of activity, or is it a property of the confluent system itself? So just to understand this aspect, we go to a much simpler system and study the rheology in the presence of thermal fluctuation. So this is a system, Vertex model, as I discussed earlier. And here we apply shear in the x direction, and the gradient is in the y direction. We set this activity to 0, but there is thermal fluctuation, and with temperature T. We take a 50-50 binary mixture with average area 1, and we need to have this T1 transition where we take this parameter L0 as 0.01. We have also done these stress-controlled flow curves where we have set B to 1, this frictional, damping parameter. And this is how we calculate the stress in the system. We have this Hamiltonian, and then stress will have two parts, hydrostatic and the shear stress. So the shear stress is most important for our purpose, and this will be proportional to the P minus P naught. So if the perimeter satisfies this constant such that P equals to P naught, then there will be no stress. But if it does not satisfy for some reason, then that will lead to the stress. We focus only on the shear stress part, sigma x to y. Now, as I said, that the perimeter term not satisfying the perimeter constant is very important to lead to this non-zero stress. And when Pi equals to P naught, then there is no stress. But if it does not satisfy the constant, then that will lead to stress. So we have looked at the deformation of the cell. So deformed cell will have larger perimeter. When there is no shear, then the cells are randomly oriented. Their aspect ratio is small, and then they can satisfy the constant. There is liquid regime. And when we apply the shear, eventually the cells elongated. Their perimeter becomes larger, and then they start aligning along the direction of the shear. And with the larger shear, again, it aligns more and more. Okay, now first let's look at the T equals to 0 scenario. And here we see that there is no shear thickening in the system. It only gives shear thinning. So these are the stress as a function of gamma dot, and these are the flow curves. We can define the viscosity as sigma by gamma dot, and this shows only shear thinning in the system. There is no shear thickening. However, this picture quite dramatically changes as soon as we include a small thermal fluctuation, and in that case, we actually observe shear thickening. So it goes, the sigma is small, and then there is a abrupt discontinuous jump, and then it goes to the solid regime. If we plot eta as a function of gamma dot, it also shows this abrupt jump. So this is the liquid regime, where the eta is constant, then it jumps, and then it again becomes this shear thinning behavior. This jump we can try to understand because in the presence of temperature, there is a finite relaxation time, tau alpha. If gamma dot is very, very small, such that gamma dot inverse is much larger, then the deformation can be relaxed by the cell. So therefore, it will still be in the liquid state. But as soon as gamma dot becomes larger, such that the gamma dot inverse is larger than tau alpha, then the cells cannot relax their deformation. And in that case, it will start showing the stress, and that will be the solid-like behavior. But it still does not explain why it should be DST. We have also done this stress-controlled simulation, and in this case, it reveals this classic S-shaped curves, which is a signature of this discontinuous shear thickening. Okay, now let me introduce this constitutive model, and the strategy that we are following is very similar to Wertkett's model, where it appeared in 2014, PRL. So we basically interpolate in these two different rheology. But the mechanism of this interpolation and the details of these two different rheology are quite different than the Wertkett's model, than the dense suspension. So we have a liquid regime. In the liquid regime, this stress comes as eta times gamma dot, and eta I can use this Maxwell-like relation, and I can write it k tau times gamma dot. Now from glassy dynamics, we already know that tau behaves like P naught minus P naught m to the power minus alpha, and P naught m basically coincides with the jamming transition. And therefore, for the liquid regime, I can write the stress as sigma L going as A gamma dot divided by P naught minus P naught m to the power alpha. In the other regime, in the solid regime comes because of the shear rate such that the cells cannot relax their deformation, and so gamma dot inverse is less than tau. And in that case, similar to this T equals to 0 system, we see a Herschel-Berkeley-like behavior. So therefore, we can feed this sigma S in the solid regime as the sigma Y, which we see linearly proportional, and then there is B gamma dot to the power n. Now we look at the data and try to obtain these parameters. So these are the parameters. The detailed values are not important, but we can actually, this fit is quite good in both regime, and then A, P naught M, alpha, etc. Those values we also obtain for both side, liquid and the solid sides. Now we'll have to interpolate between the two different rheologies, and here we need some reference points. So in the liquid side, I can write the stress with respect to some reference point, PLC, so P naught minus PLC to the power minus beta. In the solid side, I can also write with some other reference point, PSC, so P naught minus PSC to the power minus beta prime. In principle, beta and beta prime will be different, but for simplicity, we can choose them to be same. So we choose them same as beta. And therefore, I can write the distance from the critical point, the liquid side critical point, as sigma L to the power minus 1 over beta. And in the solid side, I can write as sigma S to the power minus 1 over beta. And now we want to interpolate between the two. So f of sigma, this function basically gives the fraction of solid cells in the system. Yes.
So the stress diverges? I don't understand.
No, it doesn't have to diverge. It's just that it actually it can go to a constant value. In the liquid side, this behavior seems to be very good. Here, there will be a constant actually. But it doesn't have to diverge. Still, I can get a reference point. Within this regime, it has a increase.
I'm still slightly confused. The yield stress can do weird things at a critical point. But what do you mean by liquid and solid stress?
No, so this is within this regime, what is the behavior? So if I
as a function of?
P naught. At a particular gamma dot, it actually increases.
At a particular gamma dot?
Yeah.
Okay.
We can discuss this point later. So now f of sigma gives this fraction of the solid cells in the system, and then we can obtain the average stress as sigma to the going as P naught minus some other reference point to the power minus beta. And this average PC average I can get from this PLC and PSC. And so this is this solid liquid side, 1 minus f of sigma PLC plus f of sigma PSC to the power minus beta. So I can rearrange these terms and can write the average stress in the system as 1 minus f of sigma, sigma L to the power minus 1 over beta, and f of sigma, sigma S to the power minus 1 over beta and to the power beta. Now, beta is a free parameter. There could be, in principle, 3 different parameters, but all of them we have taken same for simplicity. And we see that beta equals to 2 actually gives a good representation of the data that I'll show in a couple of slides. Now, to write down this theory or to look at the predictions, we need some f of sigma, and it should typically have a sigmoidal nature. And we have seen that several forms actually give us discontinuous shear thickening, this characteristic S-shaped curve for this system. And one possible form is f of sigma 1 minus e to the power minus sigma by sigma c to the power delta. So let's take delta equals to 1 and sigma c some value. Here we have, for this plot, we have taken 0.008, and these are the prediction. However, sigma c should not be constant for this system, because we know below this 3.8, it should, irrespective of the sigma, it should always be rigid because it's the solid side. And for a large value of P naught, it should always be liquid. So therefore, we expect sigma c to depend on P naught. So what we did, instead, go to the simulation data and try to fit the form of sigma, average sigma, including sigma c and delta as fitting parameters. We see delta equals to 0.6 gives a good description of the data, and sigma c actually does depend on P naught. Okay. And so here is the sigma c as a function of P naught, and we fit a parallel type form. So this has this form. Using this equation, these are the flow curves that we obtain using this model. Now, this is the comparison with the data, and this is the comparison. The lines are the models, and the symbols are the simulation data. The solid symbols are the stress controlled data, and the open symbols are the rate controlled data. And the agreement is quite good, given all of these many different parameters in the system. This is the comparison for the phase diagram. And in this regime, we see this discontinuous shear thickening, DST. After that, it follows by a continuous shear thickening. And beyond this value of P naught, and for this temperature, it is 3.97, it shows liquid-like behavior. This is this jump in this stress for this as a function of P naught for the discontinuous shear thickening regime, and these solid symbols are these. So these pentagons are the data, simulation data, and the blue circles are the model prediction. And this line we need to understand in a more detail, but the symbols are the simulation and the model parameter. Now we can go to the temperature P naught phase diagram, and here for a particular value of P naught, we have all of these flow curves, and from the flow curves, we basically draw this point. If it is, if there is no shear thickening, then it's a white point. If there is shear thickening, then it is colored. But if the slope is small, then the color is more fade, and if it is DST, then it is darker color. So we can now do it for the entire phase diagram and get all of these points from the simulation data. And we see that so this is the sort of scenario, that if P naught is smaller than this 3.823, this jamming transition, then there is no DST, then there is no shear thickening in fact. And all of these points are white. There is a DST in this regime at low temperature, but larger than P naught, and then there is a regime where it actually stops being DST, and then it also shows CST, so DST followed by CST, and then eventually at larger value of T, there is no shear thickening. So I can summarize this scenario in a sigma P naught phase diagram. So there is this line around which we get this DST, then it follows by continuous shear thickening, and then there is this line sigma y going to 0 line, beyond which it becomes a liquid. And then this line actually depends on temperature. So here is the sigma y as a function of P naught for different value of temperature. As we increase the temperature, then this line shifts in the left direction. But this is the jamming line, it does not shift. So what happens that if I go to higher and higher temperature, for example, let's say T2 higher than T1, then this line shifts in the left side, and it also shifts this DST regime, so it becomes smaller. Then even for higher temperature, then it again shifts left, and then this loop becomes even smaller. And eventually we expect that this loop will become simply a point, and DST, and in fact shear thickening will be completely gone. And that's the regime where we should see the shear thickening. So to conclude, we have developed a constitutive model for the discontinuous shear thickening in the system. And so this is basically interpolation between the liquid-like and the solid-like branches based on 2 reference points. And the essential ingredient for the shear thickening in this system is that this shear modulus vanishes in this regime, but the yield stress remains non-zero. So this is the regime which leads to this shear thickening, and below in certain regime of that, it gives discontinuous shear thickening. And some presence of fluctuation, whether it is active or thermal, is extremely essential. So all of these arguments that I presented will also go through for the active system as well. And so it doesn't matter what is the type of fluctuation, DST will appear as soon as we have some fluctuation, but eventually it will again go for large enough fluctuation, the shear thickening will go away. So this fluctuation basically allows this interpolation between the 2 different regimes, the liquid-like and the solid-like regime. Thanks.
Thank you very much. I see 1, 2.
Well,
So let's start.
I had it.
Okay.
Yeah, but you can go, Shan.
Yeah. Nice talk, sir. So for frictional shear, discontinuous shear thickening, you have also, when you get DST or strong shear thickening, you have increase in normal stress. I was wondering if you measure stress along the normal direction, have you observed anything?
So we haven't got into that detail yet.
Okay.
But yeah,
we can talk about it.
You might want to compare this to DST, but it seems this system is more similar to these experiments that Zvonimir Dodik and Dan Blair did in microtubules. So essentially there's an internal activity which breaks the solid-like fractions. So basically there's a competition between an internal activity rate and an external shear rate. And what that controls is the fraction of microtubules that actually behave like a solid because they span the system. And so I think this is more similar to that. There's a non-monotonic behavior there too. It's not because you're interpolating between solid-like fraction and liquid-like fraction.
Yeah.
It's very different from DST. Because DST, you go from one flowing branch to another flowing branch.
Yeah, so I may have misrepresented. I don't mean that this is happening because of the two flowing branch. This is actually interpolation between the liquid-like behavior and then the solid-like behavior.
That's precisely what I'm
Yeah.
saying. So it's more similar
Huh.
to this other known active experimental system where there are microtubule bundles that can be broken due to external shear.
Yeah.
So the external shear then controls the fraction of microtubule bundles that remain intact. And that shows a complete non-monotonic viscosity, etc. So I'm just saying, I think that system is closer to you than
Yeah,
the
that's
DST.
true. Okay. I'll have a look at it.
Thank you. Again, yet another proposal of what it might be related to. So if you take network models and here then they stiffen, and as far as I understand the vertex model, it actually inherits quite a lot of these properties. So for example, if you stretch it before doing Q1, this stiffens very considerably. So I always understood this sort of no stress and then suddenly it going up as a manifestation of this. If you try to recast the argument in a way like this, but in a way it's the fraction of contacts which are bearing, junctions which are bearing a force. And I think that's mapped in some way to what you're doing.
Yeah, so the network model, there's some sort of relevance, and also we did some calculation for this aspect ratio in this system, but haven't compared it in that detail. So the aspect ratio argument actually goes very close to this network-like systems. That's true.
First three. No, three, Peter, then you, and then Martin. And then you.
Yeah. So, may I?
Yes.
So, Saroj, I am a bit confused about this shear modulus vanishing while the yield stress remains. I mean, is this like what I expect when I have a shear jamming scenario where up to a finite strain I have zero stress? Can you explain that?
Sorry. No, I guess you are talking about. Okay, in fact, yeah, so sorry. Yeah, even this one, right? Sigma I going to 0 in a regime. So at around say 3.8, so when you have this jamming, so there is this deformation of the cell, and but say P naught is larger than 3.8, say 3.9. So even the deformed cell will sort of satisfy that perimeter constant, and in that case, shear stress will be 0. But as I now start doing this shear, then I'll deform them more and more, and eventually this will not be 0 anymore. So in the steady state, they will never be able to satisfy this constant if gamma dot is larger than some certain value. So that basically leads to this Herschel-Berkeley-like liquid within this system.
Okay. Yeah, I have a. Okay, I'll ask later.
Peter?
I have maybe a simpler version of Sri's question. So given that you're looking at steady state flow curves, not finite deformation, where in those flow curves does the modulus show up? Because you said that was essential, but I didn't really see how the modulus affects what's happening under steady state shear.
No, in the steady state, it's only sigma y. So G needs to be, in the regime that we see this DST, it is this regime where G is 0. So if I do not do the steady state, but just do this initial shear state startup. But that's the regime, that's what I wanted to mean.
Okay,
so
I
G
see.
does not appear in
Okay, fine.
Okay, Anna?
I think it's similar to what Silke asked, but have you looked at the polydispersity of the shapes as you move across the transition?
Oh yeah, we actually looked at the distribution as well.
Yeah.
This is actually what I exactly derived, and it works quite well. So I did not present that
No,
part.
but does it change across you?
It does, yes.
Yes.
I mean,
Do
in fact,
you have-
yeah, so
yeah.
one of the, this is very complicated, too much information in this. So this is this is the distribution. So this is along the direction. This is and then this line, this color is the distribution of the aspect ratio of the cells. And yeah, so how many of the cells? So that basically is the length of these arrows. So all three of them stacked into this, but we have looked at that distribution.
Saroj, very nice talk. So this G equal to 0 window, will you see this in experiments at all? No. The reason I ask is you motivated it with the actomyosin cortex that gives you rigidity at the level of a single cell. And then how does it vanish when I go past 3.81? Which means the subsequent result of shear thickening, which requires this as an ingredient.
Yeah, right.
Am I not likely to see it at all?
Yeah, no, so this, yeah, it's a very good question actually. And so what has been shown by Guillaume Chorus' group that there is this, increase of stress or shear steepening, but G becoming 0, I don't know of any experiment that has been shown. Maybe you can tell us later.
Okay, last quick question.
Saroj, when you shear it at, in the steady state, do you see development of pneumatic ordering? Because their cells are becoming elongated.
Right, yes.
And then, is it a way to understand why you get a shear thickening? For example, when you add noise, instead of basically they are aligned, the stress will be low. But if other fluctuation, if you add, then it will try to break that ordering. And then can it lead to jump in the stress?
So we haven't done the detailed analysis, but there is pneumatic ordering. The cells do get distorted, and they more and more align. So for example,
yeah. So if you look at that point of view and add, let's say, if you have a pneumatic liquid crystal and shear it, the shear stress is very low. Then if you add enough noise to break that liquid crystal structure, then your stress again goes up. Can that be a way to explain the jump?
We haven't. So this is the theory that we have developed.
There is one more.
Okay, so let's move on. Thanks again. And so next speaker is Silke Henkes.
Sorry. Okay, let's hope. Yeah, it's okay. It should be working. Okay, can you hear me? No. Is this on? Yeah. Now? No? Okay, I'm putting it closer. Any luck? I can use, or I'll use this one. Okay. Any better? Okay, good, yes. So yes, I would like to thank the organizers for inviting me here. And yeah, in this very nice and historical place. And I'd like to essentially pick up where the last two speakers started. So they very much thank you. You gave all of the introduction I needed, yes. So I want to talk about emergent motion patterns in active solids and glasses. And this is motivated by cells. So as we've seen already, collective motion of epithelial cells has attracted a lot of attention over the last, at this point now, 15 years. And I don't want to make a long introduction. I just wanted to point out two highlights, is that you tend to get correlated motion patterns and correlated traction patterns with a substrate. And these are very generic. For example, this is a famous paper on MDCK, one of the first ones, from force traction microscopy. These are human corneal epithelial cells of my former student Kaya. And even in real developmental systems, like here for a chick embryo, you see the same things rearranged in a rather complex manner. Now the question of what is this, where does it come from, does it mean, has had many answers over the last couple of years, including actually quite a school which interprets this as an active pneumatic with emergent topological defects, and to such a point that people classify it as a type of active turbulence. So active turbulence is not turbulence in the normal way, and is really a misnomer because there tends to be a length scale associated with these things, and you get them in bacterial simulations in the famous microtubule kinesin active unstable pneumatic system, and indeed in tissue monolayers, where you can see them here. And this sort of swirly motion has been remarked upon right from the beginning. And when I looked at this first, sometime around 2010, I said, this looks like a sheared kind of rheological material of colloids or something similar. And in fact, I'd like to convince you that in fact that these correlations do come from something like this, and that this makes a very good null model for epithelial cell sheets. Specifically, you can see here this is a dense active Brownian particle liquid. These are the velocities, they're spatio-temporally correlated. And I will show you how this matches. And I'll go from there then in a second. So, okay, let me show you. Yeah, I'll explain that where the correlations come from, how we apply this to this very nice system which has a boundary. And then I would like to move on to two much newer results which go beyond this. One of them where you start to align the direction of self-propulsion with the internal mechanics of the system, so it's called self-alignment. And then the second one where you actually put stresses instead of self-propulsion into the system as appropriate for 3D systems, for example. So let me start at the beginning with a simplified situation. So let's take everybody's favorite model, active Brownian particles. So the idea is that you have overdamped Langevin dynamics. Here the self-propulsion comes in as a force, so as V0n in some direction and with an angle theta. The rest of the interactions are short-range pair forces, and the angle of n, theta, only does rotational diffusion and absolutely nothing else. It doesn't couple anything with anything, yes? And, huh? Oh, yes, thank you, sorry, yes. So because of this, you can solve this equation, and you can map this to a essentially time-correlated active driving or memory kernel, where the NN correlation function is e to power minus delta t over tau, where tau is the persistence time, 1 over the rotational diffusion time. And I should say, Olschen-Uhlenbeck driving qualitatively is extremely similar. It has the same internal correlation time. And because of this, if I go to Fourier space with this, the correlation function of n is a Lorentzian, independent of q, because this is locally correlated only, and with a weight set by the persistence time. Okay, so far, so basically obvious textbook idea, but this has an interesting consequence once you put it into an elastic system. So what happens is, and I've done this here in 1 dimension just for simplicity, if I take an elastic system with here u is the displacement field, and u dot is the velocity, with a stiffness kappa, so Laplacian u, 1-dimensional elasticity, I can solve this thing exactly in Fourier space, and so I can calculate the V correlation function. As you can see, it's going to depend on the NN correlation function. I stick this in, I get essentially convolution here, multiplication in Fourier space of the elastic part of the equation and the colored noise of the equation. Okay, so I put these two things together. You can see this gets modulated. Something complicated happens here once this gets larger. This here still has diffusion in it. And once you go back to integral to frequency, you will get an equal time correlation function, which has a length scale in it. A length scale, which is given by the square root of the stiffness persistence time over friction coefficient. And we says the velocity correlation functions decrease above this length scale. So I should say if this was a thermal system, this V of Q would just be a constant here, equipartition essentially. And so this is a purely active effect, and you can think of this as if I'm pushing persistently in overdamped elasticity, I will propagate diffusively in overdamped dynamics, and how far do I get in persistence time tau? Exactly this far. So that's where that length scale comes from. Okay, so that's a simple calculation. But you can use this to really, I think, gain insight in what's going on in some of these systems. So we started by looking, well, at dense ABPs at ABP glasses. And so the idea here is that we can, in fact, approximate our system by this sort of formalism by saying, okay, I am going through an energy landscape, and if my alpha relaxation time is long enough, I'm stuck in a minimum for times which are longer than the persistence time. If that is the case, I can do a linear response calculation. Here is the dynamical matrix. And I can do the exact same calculation using normal modes. And I should say Manuel Lemaitre, Craig Maloney did very similar work a while ago for sheared systems. And if you carry this out, you will get an energy spectrum which is not equipartitioned. It's formally broken. It depends on lambda mu, and it depends on the persistence time here, so that it gives less and less energy when the mode is large and the persistence time is large. At short persistence time, you recover the equipartition with an effective temperature, the standard active temperature. So you do this, and you can, as I said, do this formally in continuum as well. So I've gone back to 2D now, so because most of our systems are 2D. So you do the same sort of calculation I just showed, and you get the same thing twice, once with a longitudinal and once with a transverse length scale. And once you do this, they both got like square root of tau. And I should say, this has been around as an idea. I'm not the only person who looked at this. Actually, quite a number of people in the audience here have worked on this and have looked at different aspects on this. And in fact, something which is very nice is that it seems to extend somewhat further also into a liquid phase. And we looked at this already at the time here. So this is ABPs. This is the sort of patterns you get. So you see the strong spatial correlations. And as a function of persistence time, here this is in the deep in the glassy phase, you get an emergent correlations. This is from the first neighbor peak of the structure factor. And the dots are simulations. The continuous lines is the normal mode spectrum, so linear response formally, and it works very well. And the dashed lines is the continuum, which works very well, except at larger Q, as it shouldn't. And the interesting bit is this stuff actually, here this is intermediate, and I'm changing the effective temperature, so the bottom four of these are liquid. And it works rather well in the liquid phase until the last two, where the alpha relaxation time becomes shorter than the persistence time. And in fact, this has been further quantified extensively by actually Jan Keta, and he was working with Ludovic Berthier and since. So that's old stuff. So let me show you some newer stuff. So what we've applied this to recently is this particular system. So what you're looking at here, let me see if I can get this to play as well, is MDCK cells moving into a new area. And so this is on a glass slide, you remove a stencil, and then this grows. So this has been known as what's called a fingering instability in these systems for a long time. And so this is very nice data from the group of Inke Netke in Dundee. And so my student Sander analyzed this, and you can see the edge here, how it's moving, and you already see the very strong and correlated spatiotemporal fluctuations inside the sheet. Yeah? And I should say, we're not the first people who looked at this. In fact, there is rather a cottage industry of people who have proposed models for this. Yeah? And if I'm being slightly blunt, everybody's favorite instability gets their day there. So it's maybe it's chemical signaling or curvature enhanced motility, velocity gradients leading to accelerated response, pressure dependent growth rate. There's also KPZ formulation in here. And I should say separately that there is very good biological evidence that there are leader cells at the front of these fingers, so cells which have a different phenotype. And then the question is, are they strong enough to form these fingers and drag them and generate this? And the answer appears to be most recently actually no, including by very nice work of Medhavi Vishwakarma, who is here now at IIC from a couple of years ago. So what we'd like to do here is see if we can make a null model. So if you have spatially correlated cell movement inside, as we know we do, and an actomyosin cable around the edge of it, how much of this do we actually get? So how much of the phenomenology is explainable just by this. And I wouldn't be giving this talk if I don't think that the answer is actually a lot of it, yeah? So what we do, null model, is we adapt a self-propelled Voronoi model. So thank you, Saroj, for introducing this one in detail. So the idea is the same Voronoi model. So Voronoi model, as you remind, every cell is a Voronoi tile. It's driven at the center with a self-propulsion active force, which is doing rotational diffusion, ABP, the usual thing, yes. And the energy of the vertex model is given by balance of an area constraint and a parameter constraint. And I should say we're always on the solid side of this thing, and we melt this by driving. And so one thing we added compared to the normal classic situation is we added dissipation between cells. So if you think the first term in hydrodynamic friction or viscosity in continuum, and which turned out to be extremely important for what we're looking at. So we generate this model, and we used actually our old code where we did something at the time actually very clever by Raskus Knepnek, which is generated a boundary of these cell sheets. So the idea is that we're in a Voronoi tiling, and the cells are actually moving, centers are actually on Delaunay triangles. So these are dual to each other, and you need to be quite careful in constructing this. And if you're even more careful and a good computational physicist like this, you can make a border here by closing Delaunay triangulation, then physically interpret the border by making it a spring, bead spring type polymer. So there's a potential on this border which has a stretching spring and a bending spring. The stretching spring has rest length 0, so this thing is always under tension. So this is our crude model of a contractile actomyosin cable. I should say it's viscoelastic because it can create and remove nodes when cells try to cross this border in a triangulation. So once we take all of this, we simulate the system, and I'll show you the final result, because this is after we match parameters, and I'll tell you how we did it, okay? Yeah? Yeah.
Where are the actomyosin cable located physically? Like, are they at the edges, or are they inside the cell?
In the real system, they're at the edges, yes. Here, they're sort of in the model that like have a cell outside. So this is of course not exactly. And if you would want to use a real vertex model for this, this would presumably work equally well, at least.
Okay. So these are the branched actin or the linear actin?
Okay. So you made experimentally. They are on the outside. You can see it here.
Okay.
Along the outside rim, yeah.
Okay, thanks.
Yeah. Was there a question? No.
So only the friction is pairwise, not the active forces.
No, only the friction for now. You'll get the rest later, yeah. So I want to say instead, in fact, you have to be careful how you simulate this because it's an implicit equation. Now you need the eigen library to invert this, so it gets computation a bit more tricky, but you can do it. And so eventually, here, this is what the system does. So you can see that I promise you there is no instability, there's no nothing. This is just active Brownian driving, a vertex model, and a boundary, nothing else. So you can see here, the red arrows is the velocities, and you can see very strong formation of fingers here. I should say our system doesn't have cell division or compression or flattening, so we're not actually spreading outward, okay? This is something you can add, but it's tricky in this particular model. So you can see we have the nice internal correlation functions. And so we actually managed to understand what is happening here. So, huh?
So it's a fixed area.
This is fixed area, yes. So we can understand the interior. So what we did is we extended the model which I showed you right now by adding essentially internal dissipation. So this is compressive and shear viscosity. This is the bulk and shear modulus as usual. The same active Brownian driving. Then if you, at that time postdoc Jan Keta, you can solve this thing. It's a longer calculation, but you end up with a real space correlation function, which is a combination of Bessel functions. These are known, these are not fit parameters. Sorry. 1 second, I need to... Sorry, that was too fast, yeah? So, okay. So you have this, and this is set by 4 correlation lengths, yeah? So it sounds a lot, but it's not that hard. So you have 1 and 3 are active. So you're seeing the same persistence time over friction times elasticity, modified a bit by the viscosities. 3 is for shear. 2 and 4 are hydrodynamic length scales. So they're related to the ratio of the viscosity to the friction with the substrate. And these turn out to be important because, though this looks complicated, if you actually plot this, this is very close to an exponential. And you can see it here in orange, yeah? In black is the experiment, in green is the simulation. And here in purple would be what would happen if I didn't have pair dissipation. So you get actually a jump in this, and they need to do a regularization. Yeah?
So when you showed the picture of the fluctuations without any correlations or anything, does the spectrum of fluctuations also match what you would see in experimental?
Yeah, wait. Yeah. So you can also compute this in time, and it's here is slightly different, but the actual simulation matches. So there is something complicated about melting going on, which relates to this. And we measure mean velocity, and then we iterate to get this to work. So I won't go through the whole thing here, so I can show you the spectrum afterwards. But we managed to map the border to a... Sorry, I don't know what it is today. I flew through Delhi, which had absolutely horrible air. No, it's okay. This is so okay. So we mapped this to a model of a polymer at an interface. So the idea is that we can write dynamical equations where we have overdamped height dynamics, so one-dimensional model of the interface. We have a line tension in it. We have a bending stiffness. So these first 3 terms, that's just overdamped dynamics for a worm-like chain. Okay. But then, okay, we add the pair dissipation to be consistent with the rest. And we put in active driving for the interior. And if I put this, so you can see here, this is a tiny simulation, that you get a growing, essentially, roughness of this thing. And you will see this grows with time, and it coarsens, actually keeps coarsening indefinitely. And you can see something which looks very much like the fingers appearing and disappearing, with a time scale, I should say, which is much longer than this. Now, I'm sorry, I'm not going to tell you exactly how we compared this to each other, but it works, and we understand the length scale and the time scale. It's set mostly by the interior fluctuations, by relaxation at the scale of a finger. Just wanted to show you visually, and then I'm happy to discuss later, that in fact you can get, here's boundary traces from experiment, from the simulations. From the height equations, I should say we have shifted these by the mean velocity, so you can see the similarity already. Happy to talk more about this afterwards, because I just wanted to switch gear on something different, yes? And so everything I've shown you is so far is a completely minimal model, which is just active Brownian driving, yes? But obviously there's more going on in systems. And so the first one I wanted to tell you about is, in fact, self-alignment or coupling to forces. So this idea has been around for rather some time, and it started, for cells at least, with Szabo et al. 2006 for flocking migration for keratocytes. And the idea is that you can reorient with a total force exerted on a cell or migrate along a stress gradient, sometimes also called pletotaxis. So the idea is very simple, that in my equation for my angle, in addition to just noise, I also have alignment of my angle with my angle of my velocity. And so the thing can reorient. So think of a human being pushed in the crowd, and then you reorient with the direction you're being pushed. Okay? That's all it says. And in fact, if you put this in confinement, it systematically oscillates. And if you put this in free boundary conditions, it systematically flocks at strong enough alignment strength. And I should say this, this is from our model, SPV, yes, with a couple of collaborators. So they actually looked at this model, and so here, in a one-dimensional system of MDCKs here, and where they saw persistent oscillations, they actually managed to at least qualitatively explain this with the same flocking oscillation model. And I should say, this was sort of a curiosity for many years, but it has recently attracted a lot more attention because people combined this, originally Olivier Dauchot and Paul Bacconnier, with this sort of actuated material metamaterial, where they found in a small lattice system with self-propulsion with these Bristol boards, which are self-aligning, that it makes the same oscillations I just showed you. And even more recently, this is the group of Denis Barthelot, has said this happens in crowds, actually something, in fact, I think I'd long suspected. The same sort of oscillations, of course, with much more noise and with more rheology and more rearrangements. I should say, in fact, a long time ago, you can see this here, got rejected from PRL. I should have kept it, yeah? We explained this as a very long time ago as the selection of the lowest available normal modes in this system using linear response theory, yeah? And you can see here, this is numerics on the same sort of circularly confined system. You can see this is projections. You can see a stark spike. Whereas here in this system, at least, the mode selection appears to be highly nonlinear, depending on the structure and the boundary conditions. And so essentially, I should say we wrote together a review article on this, which cites all of the existing literature on this until 2024, including a paper of Masaki-Sano from 1996, which even he had forgotten about, apparently. So there is more there. Here, please have a look. But there's something that has bothered me always, is that this seems to be highly complex and nonlinear. This was linear response calculation. I don't think what I've done recently is started to revisit this more carefully. So this is unpublished work which I'm doing my student Sander. So this is this classic confined polydispersed system. This has very high density in the aligning phase. And you can see this is the type of oscillations you get again and again, yeah? So it's periodic, but it's not perfectly periodic, as mean there's fluctuations in here. And so we can actually try to understand this by using Ito calculus carefully. And I should say there is a lot of recent work, especially around Lorenzo Caprini, who uses very similar tools to this. And so the idea is that, let me play this again, it's a fun movie, that, okay, I do a linear response calculation, this Hessian matrix here as before. Then any angle, using E2, you actually can realize you have Jn cross V cross n in there. You have the noise, but you also get an extra -1 tau n term, which people usually don't write when they do it numerically because you renormalize the n anyway. But if you keep this properly and stick this one here back in that equation, take one more derivative, and then go to normal modes, you can in fact write down a second order self-consistent equation for the modes amplitudes. Yes, okay, I'll speed up, yeah? And it's a bit complex, but you can see some things already. So you have the U dot here is a derivative of the total elastic energy, which is in these disordered systems likely constant, so we're going to drop this. And that's the only real nonlinearity here. We assume that the mean velocity of a particle is constant to get there. And we have some horrible multiplicative noise projected onto modes, yes? So we got stuck there for a little bit. And then we said, let me try the simplest thing. Let me assume that this, we can approximate this again by white noise, which is actually exact in the limit of an ABP. In an ABP, this is exactly white noise, and the oscillating more complicated. I dropped the nonlinear terms. I'm ending up with a damped stochastic-driven oscillator, which is actually the same thing we had all these years ago, except with noise now. There's a phase transition between oscillating and non-oscillating. It's a function of the combination of J and tau. And there is a number A, which is the ratio of V to V0, which is smaller than 1, which is a very important internal parameter. So the only tuning knob we have left now. Now if you have this, I can compute my mode spectrum again, and here it is, and you can see this is interesting. So there is you see the lambda to omega, this is a propagating wave, and which sort of gets amplified at this point, so you get lots of modes velocity at a propagating wave, and this term here smooths the divergence, but only if this term doesn't make it doesn't cross zero. So I should say that is, you see the damping terms, you can see there should be some sort of J combination for every lambda, some combination where this goes to zero, yeah? This would be the amplified wave in this thing. And I wanted to say limit J going to zero, you get the ABP result. And last thing I wanted to say, for fixed everything else here, you can see that this will always go to zero, that for this cannot be negative, else your system blows up, yeah? So it has to be positive or zero, and it's exactly zero at the lowest mode then, is the only condition you get out of this. And in fact, if you solve this, you can say, for an oscillating system, you fix the A such a lowest mode is undamped, and here's a simulation, here's our linear theory, and you get propagating waves in here with this frequency which depends directly on the stiffness here in continuum, the alignment, etc. For the diffusing side, we're still working on this. Simulation and theories, you get something which is much like active Brownian dynamics. So you can see this sort of diffusive square root in here. And in fact, this approximately maps to active Brownian style dynamics with a renormalized correlation length and time in there. So this is in preparation, not quite there. I think we still hunt the factor of pi somewhere. And if I have any time left, I don't know if I do, I wanted to very briefly tell you about work of Jan to try to understand cell-cell stresses. So I should say cell-cell stresses are obviously everywhere. Most active forces are between cells, and they're probably responsible for these defects if they're there. And for example, we looked at this by using vertex models with feedback and tractions on junctions. Of course, this was horribly complicated. So instead, Jan said, let's look at the simplest model. So let's look at what the simplest model is, which is Ornstein-Uhlenbeck junctions. So tension on the junctions on top of the vertex model, which have persistence time scale, and they're zero on average. Now, this led to something somewhat unexpected. We found active stress fluctuations. Now, essentially, this is a symmetry. So the symmetry is that you're on a dissipative structure, and you come gradient of a potential, and then these active forces or active stress fluctuations can be written as divergence of a stress tensor by definition because they're pairs of balancing forces, okay? So we call this lambda, and this lambda for the AOUP, or what we call pair ABP, so symmetrized version of active Brownian particles, have the same time correlation as ABPs, but they have a Laplacian in front in space because of the pair correlations. You can also write this in discrete, but it is the upshot of that. I should say this breaks FDT in irretrievable ways. There's no thermal limit of any of this stuff. Now we look at this, and we found something. Okay, we measured the psi 6 and what's also called the Q0, so the equivalent translational order parameter, and found the first order phase transition in these, with both of them actually changing together. For example, here you can see this is our coexistence phase. So we looked quite hard, and we're pretty certain it's first order. And so I'm showing you most of the results for this pair ABP because it's numerically easier. So you can see the transition here. And we found something weird. We found a mean square displacement, which goes between solid and liquid, with a region in here, which is liquid but stays crystalline on average. So it's diffusing vacancies and stuff, which make this happen. And the interesting bit is if you do that same sort of theory, as I've told you a couple of times, now extend it to the active stresses. So the vector forces, you've seen this already, V of Q, there's a Q square in front, this would be displacement field. Flat down, yes, selection of a length scale. This one here, there is an extra Q square and everything. You get up, flat. So this is a weird one because it suppresses fluctuations at long wavelengths and keeps them at short wavelengths. And because of that, this system acts different from other two-dimensional systems. Because of this suppression, you get bound displacement fluctuations, and whereas you would get the usual log divergence if you use forces or, for that matter, thermal systems. So you get a constant you can numerically check this. So here, for example, PREP, this is the force type, the stress type is really, really constant. And because it's the same thing, at the linear level at least, you will get long-range order in 2 dimensions. Because this is legal, doesn't break Mermin-Wagner, we're not thermal, you suppress these fluctuations. So you get a constant with an exponential related to the MST plateau, whereas you get a power law usually. Here, this is the approximate power law for the force system. For the stress system, as you can see, this is the flattest flat curve I've seen in my life. And also, this thing is hyperuniform. You can compute the structure factor at linear level, and it goes like Q square, whereas the normal one for force or thermal goes like 1, which you can see here, it flattens out eventually. This one here, let me explain a little bit because it's a messy plot. You start in a solid phase. This is Q squared, actually goes down a little further. I think these systems equilibrate very slowly, so that I wouldn't bet my life on. In the transition region, you're not hyperuniform because you're mixed, you're first order, you have a system which is in patches. Then you become again hyperuniform in the disordered phase. And so that was really interesting. And if I might end with actually something slightly ironic is, while this is really cool StatMech, this makes for absolutely terrible tissue model because you cannot get any collective motion with these systems. And we had written this originally for sort of cell spheroids in 3 dimensions. So we've been since gone back and tried to understand how do you make collective motion properly in 3 dimensions. And so you can be, so there's a number of different options. And I want to say, please look at the poster by Chinmay here this afternoon. He can tell you more about this. And so with this, I would like to thank everyone, especially the students involved, so Sander, postdoc Jan, Rasko, Inke, everybody involved here over the years. Thank you. Yeah.
Thank you very much. Questions? Yes.
Yeah.
Sorry.
Yeah. Yes.
Driven by activity, or is there cellular growth?
So 1 second. Yeah, I probably shouldn't, but there is, yes, there is growth, but it's subdominant. So you're sort of like, on the time scale of the fingering, it's about a day, yeah? And cell cycle time is something like 30 hours or so. So most cells, only a fraction of cells have divided. So this appears before this happens. You can also knock out cell division, and it still happens in experiment. So we think, I mean, it's biology, always something matters to something, but we don't think it's predominantly that.
Okay.
Hi. Yeah, I have a question for.
Yeah.
So recently we looked at Mermin-Wagner in his active glasses, both with RTP and ABP.
Yeah,
and we found that in 2 dimensions you have a power law divergence and 3 dimensions log divergence, and then try to basically use the same framework that you developed and derived once more the mean square displacement as a function of system size. And you always basically recover equilibrium-like behavior with this active elasticity kind of theory.
Yeah, with the active Brownian, yes?
Yeah.
And so I should say this is a linear response calculation. Its elasticity is in a crystal. You can, of course, this is somewhat crude. And I'm
no, but it also predicts for infinite tau p, there is some sort of other power law which seems to be not coming up if you look at simulation data. So, and what we propose is that there is some nonlinear, basically dispersion relation, omega versus q. And so my question is there a way to basically somehow justify or find out where this nonlinear phonon dispersion can come in picture?
I'm not entirely certain. So we want to say ABP, this phonon dispersion relation. But this is, okay, normal modes is just this, yeah?
Yes.
So you see this is diffusive, but this is the linear level. So we haven't touched it. I don't know. I barely do stuff. I mean, I only do that sort of stuff. I don't know. I'm sure you can.
Okay, maybe I'll just discuss later.
Yeah.
Yeah, so I have two related questions. So it's great that you're in this slide. So in the previous slide, you showed this video where it started at some kind of an oscillating state and which eventually died down and became sort of non-oscillating.
This keeps oscillating.
So, but it does go into a state where it kind of freezes, right? The motion
No, that was just the end of the video.
Oh, that's the end of the video. Okay, so so then that makes my question moot. So let's go to the second question.
Yeah.
So the second question is, you try to use this active Ornstein-Uhlenbeck process to model the edges, right, of a vertex model. Can you tell me the motivation of that? That was kind of too fast.
Okay, for this one, yeah?
Yeah.
Sort of as the idea was originally, can we have the sort of stress fluctuation equivalent of ABP deriving? It was sort of, can we make an equivalent minimal model and see what it does? And both when Jan and I looked at it, we were convinced we were going to see the same correlations, and then we didn't. So that was the motivation. I should also say this has been used as a for Drosophila wings, actually by Marco Popovic, a group of Frank Jülicher, and people have mapped the melting and phase diagram of it as well, so it's a known model.
So what are you exactly trying to observe here and measure here, like, and compare with the experiment?
For this one, in the end, not much, because it turned out, as I said, because of all of the interesting stat-make of this model, I don't think it's a good model for anything collective going on.
Okay, so it is basically not really useful to study biological system.
Well, that seemed to have been the conclusion after a while, yes.
Okay.
You need some other extra connections between them, yeah.
Okay, thanks.
Yeah.
So let's have further discussions during the coffee break. Thanks again, Silke.
Yeah.
And we'll reconvene at 11:50. So.
Hi, yeah.
Okay, go ahead.
Yeah.
So I test the connection while you're
yeah. So I'll let me move the let me move the okay. Well, let me stay here. Okay, then I stay here for a bit. Yeah.
So maybe it's a shorter one.
Yeah.
So when you say it's not interesting for the collective behavior, I disconnected at that part. Why do you say that?
Because the velocity correlation length is essentially zero.
It's not your job now. Yeah, I know. I wanted to check the connection.
Yeah.